Space is an endless expanse, stretching beyond our wildest imaginations. It's a canvas of unimaginable scale and beauty, painted with the light of countless stars and galaxies. Picture a scattering of glittering diamonds on a sheet of black velvet, each one a distant sun. Galaxies appear like islands of light in a sea of darkness, each one a beacon in the vast cosmic ocean. These islands of light and energy are home to billions upon billions of stars, each star a potential sun for its own solar system. But space is not empty. It's filled with cosmic dust, gas, and unseen forces that shape the universe. It's teeming with unseen forces and mysterious objects, from dark matter to gravitational waves. Among the most captivating are black holes, enigmatic regions where the laws of physics seem to break down. These cosmic entities are regions of space-time where gravity's pull is so strong that nothing, not even light, can escape their grasp. There are different types of black holes, each with unique properties and origins. Stellar black holes are born from the death throes of massive stars, collapsing under their own gravity. Supermassive black holes, millions or even billions of times the mass of our sun, lurk at the centers of galaxies, influencing the motion of stars and gas around them. These objects are paradoxes of nature, invisible yet immensely powerful. They are invisible, yet exert a gravitational pull that shapes the universe around them, bending light and warping spacetime. Their existence challenges our understanding of physics and offers a glimpse into the most extreme environments in the cosmos where the known laws of nature are pushed to their limits. Black holes are enigmatic regions of spacetime where gravity is so powerful that nothing can escape. Picture a well with sides so steep that nothing can climb out. That's the essence of a black hole. But black holes are not mere voids. They are incredibly dense objects. Imagine compressing the entire mass of the Earth into a marble. That's the kind of mind-boggling density we're talking about. Black holes are born from the remnants of colossal stars. When these massive stars meet their end, their cores collapse under their own immense gravity. This cataclysmic collapse creates a singularity, a point of infinite density at the heart of a black hole. Encircling the singularity is the event horizon. This is the infamous point of no return. Once something crosses the event horizon, it is forever trapped by the black hole's relentless gravitational pull. Stars are the cosmic engines of the universe. In their hearts they fuse hydrogen into helium, unleashing staggering amounts of energy. This energy creates a delicate balance, a dance between the outward push of pressure and the inward pull of gravity. Yet, like all things, stars have a life cycle. Massive stars, giants compared to our sun, live fast and burn bright. They devour their fuel with a voracious appetite, forging heavier elements in their cores. But eventually their time runs out. They reach a point where fusion can no longer be sustained. The core collapses under its own immense gravity, igniting a cataclysmic supernova explosion. This explosion is a cosmic spectacle, one of the most powerful events in the universe. The remnants of the core, if massive enough, continue to collapse, giving birth to a black hole. These stellar mass black holes are the echoes of once mighty stars, scattered throughout the galaxies, silent witnesses to the universe's violent past. Picture two colossal titans locked in a cosmic waltz. They spiral around each other, their movements becoming ever more frenzied and intense. This is the epic dance of black holes, destined to merge in a dramatic finale. As they orbit, they twist and warp the very fabric of spacetime. These distortions ripple outward at the speed of light, carrying immense energy away. This energy loss pulls the black holes into an ever-tightening spiral. In their final moments, they unleash a cataclysmic burst of energy. The titanic collision results in the birth of a single, more massive black hole. This monumental event sends shock waves through spacetime, creating ripples known as gravitational waves. These awe-inspiring mergers are not just theoretical. Astronomers have detected the telltale signatures of these events through gravitational waves, confirming a groundbreaking prediction of Einstein's theory of general relativity. Picture a stone dropped into a tranquil pond. The impact sends ripples cascading outward, gently disturbing the serene surface. These ripples dance across the pond, forming a mesmerizing pattern of waves that journey outward from the point of impact. Gravitational waves are akin to these ripples, but instead of water, they ripple through the very fabric of spacetime. Envision spacetime as an immense, invisible tapestry that can be stretched and compressed. These cosmic ripples are born from the universe's most cataclysmic events: black hole mergers, supernova explosions, and even the primordial Big Bang. The Big Bang, the monumental explosion that birthed our universe, sent ripples through space-time that continue to traverse the cosmos today. As these cosmic events unfold, they create distortions in space-time that travel outward at the speed of light, carrying whispers of their origins. By the time these gravitational waves reach Earth, they are incredibly faint, stretching and squeezing space-time by less than the width of an atom. Detecting these minuscule changes is a monumental challenge, demanding extraordinarily precise instruments and cutting-edge technology. Instruments like LIGO, the Laser Interferometer Gravitational Wave Observatory, are meticulously designed to capture these tiny distortions in space-time. The detection of gravitational waves heralded a new era in astronomy, offering a novel way to observe the universe. It flung open a new window into the cosmos, allowing us to explore objects and events hidden from traditional telescopes, unveiling the universe's secrets we once only dreamed of. Detecting gravitational waves is a monumental feat of engineering and scientific brilliance, demanding the synergy of scientists, engineers, and cutting-edge technology. At the forefront of this endeavor is the Laser Interferometer Gravitational Wave Observatory, or LIGO, a groundbreaking instrument that has transformed our understanding of the cosmos. LIGO operates two detectors, strategically located in Washington State and Louisiana, to optimize their detection capabilities. These detectors employ lasers to measure the distance between mirrors with astonishing precision, down to a fraction of a proton's width. As a gravitational wave traverses the Earth, it distorts space-time, causing minuscule changes in the distance between the mirrors, a phenomenon foreseen by Einstein. These changes are infinitesimal, but LIGO's advanced technology and meticulous calibration make it sensitive enough to detect them. In 2015, LIGO made history by detecting gravitational waves from a black hole merger billions of light-years away, a monumental achievement. This discovery validated Einstein's predictions and heralded a new era of gravitational wave astronomy, unveiling a novel way to observe the universe. Since then, LIGO and other detectors worldwide have recorded dozens of gravitational wave events, each enriching our understanding of the universe. Each detection offers invaluable insights into the objects that generated the waves, shedding light on the most extreme environments in the universe, such as black holes and neutron stars. Gravitational waves are not just ripples in space-time, they are the universe's whispers, carrying secrets from the most enigmatic corners of the cosmos. These waves are messengers, bringing us invaluable information about the cataclysmic events and mysterious objects that birthed them. By meticulously analyzing these cosmic signals, astronomers can unravel the masses, spins, and distances of black holes and other celestial phenomena. For instance, the intricate shape of a gravitational wave signal can disclose the masses of the black holes that collided in a dramatic merger. The frequency of these waves unveils the spins of the black holes, adding another piece to the cosmic puzzle. Meanwhile, the amplitude of the waves reveals the distance of these monumental events echoing across the universe. Though gravitational wave astronomy is still in its infancy, it has already revolutionized our understanding of black holes and the grand tapestry of the universe. As our detectors grow more sensitive, we stand on the brink of uncovering even more profound secrets hidden within these cosmic whispers, forever changing our view of the universe. The detection of gravitational waves has unlocked a thrilling new frontier in astronomy. It's like gaining a superpower to explore the universe. We can now listen to the cosmos in ways we never dreamed possible. With this newfound ability, we are uncovering wonders beyond our wildest imaginations. We are mapping the hidden population of black holes in the universe, and we are unraveling the very fabric of gravity itself. But this is just the dawn of our journey. As our technology advances, we will detect even the faintest whispers of gravitational waves. This will enable us to study the most distant and exotic phenomena in the cosmos. The future of gravitational wave astronomy is dazzling. It promises to unlock the universe's most profound mysteries and reveal its deepest secrets.